Welcome to week 3 of building scalable distributed systems. In this week, we're going to introduce some of the fundamental approaches to scaling a software system. The types of systems we're concerned with in this course are oriented towards internet-facing systems that we all utilize every day. You can name your favorites. These systems accept requests from users through web or mobile interfaces, store and retrieve data based on the user requests or events, perhaps from a GPS-based system, and have some intelligent features such as providing recommendations or providing notifications based on user interactions. We'll start in this section by describing a simple design and show how it can be scaled. In the process, several concepts will be introduced that we'll cover in much more detail throughout the rest of this course. Hence, this section just gives you a broad overview of the concepts and how they aid in scalability. Let's start by going back to the origin of most software systems. Virtually all massive scale systems start off small and grow due to their success. It's a common and sensible approach to start with a development framework such as Ruby on Rails or Django, or an equivalent, and these promote rapid application development to get a system up and running quickly. A typical very simple software architecture for these starter systems, which closely resembles what you get when you use a development framework, is shown on the next slide. This architecture comprises a client tier, a web application tier, application service tier, and a database tier. If you use Rails or equivalent, you get a framework which hardwires a model view controller pattern for web application processing and an object relational mapper that generates SQL queries, all common components of these simple application frameworks. With this architecture, users submit requests to the application from their mobile app or web browser. The magic of internet networking, which we'll talk about next week, delivers these requests to the application service, which is running on a machine hosted in some corporate or commercial cloud data center. Communications uses standard network protocols, typically HTTP and TCP/IP. The application service runs code that supports an application programming interface, or an API, and the clients use to format data and send HTTP requests to. Upon receipt of the request, the service executes the code associated with the requested API. In the process, it may read or write from a database depending on the semantics of the API. When the request is complete, the service sends the results to the client to display in their app or browser. Many systems conceptually look exactly like this. The application service code exploits a server execution environment that enables multiple requests from multiple users to be processed simultaneously. There's a myriad of these application server technologies around. The JEE framework and Spring for Java, Flask for Python, and so on. They're all widely used in this type of application scenario. This approach leads to what is generally known as a monolithic architecture. Monoliths grow in complexity as the application becomes more feature-rich. This eventually makes it hard to modify and test rapidly, and the application execution footprint can become extremely heavyweight as all of the API implementations run in the same application service. So monoliths tend to be very large code bodies. If request loads stay pretty low for an application, then the application architecture, this monolith, can often suffice. The service has capacity to process requests with consistently low latency. But if request loads keep growing because the system is successful, this means latencies will grow as the service has insufficient CPU and memory capacity for the concurrent request volume from the clients, and hence requests take longer to process. In these circumstances, our single server is overloaded and becomes a bottleneck. In this case, the first strategy for scaling is usually to scale up the application using additional hardware. For example, if your application is running on AWS, you might upgrade your server from a modest T3X large instance with 4 virtual CPUs and 16 gig of memory to a T3 2x large instance, which doubles the number of CPUs and memory that's available for the application to execute. Scaleup is simple. It gets many real-world applications a long way to supporting larger workloads. It obviously, though, costs more money for the hardware, but that's just scaling for you. You can't avoid additional costs as you grow the capacity of your system. The other downside of scaling up is your application still has a single point of failure. If your server becomes unavailable due to failure or a network partition whereby the server cannot be seen by the clients due to a network failure, then the service is unavailable. This is a considerable downside, and we'll see how we get around this in a couple of slides. We mentioned monoliths or monolithic architectures a slide or two ago. Let's just quickly delve into what we mean here. As a system grows, typically all of the APIs are implemented in the same code body. This leads to service implementations which have millions or tens of millions of lines of code. And as these grow, they become hard to change and evolve because there's just so much code which has been developed over a considerable amount of time, months or years. As you can see in the diagram here, the monolithic architecture couples the user interface logic, the business logic, and the database interface into a single service implementation. This becomes heavyweight and, as we said, hard to change. As we move through this course, we'll contrast this approach with an approach called microservices, which are typically much more lightweight and extremely trendy at the moment. Scale-up is great and simple, but it has limits in terms of capacity. No matter how big you make your server, if your load keeps growing, it will exceed the capacity that you've provisioned. The single point of failure is also a problem, especially for systems that need to be highly available. In the past, and if you watch the video that I recommend from Adrian Cogcroft, very highly reliable hardware was available. The tandem HP non-stop servers, IBM had an equivalent. This is 10 years ago. People were promoting these as the solutions to single point of failures. However, this stuff's no longer sold because we've developed low-cost technologies that enable us to implement an approach called Scaleout. Scaling out relies on the ability to replicate a service in the architecture and run multiple copies on multiple server nodes. Requests from clients are distributed across the replicas so that in theory, if we have n replicas, each server node processes the number of requests divided by n. This simple strategy increases an application's capacity and hence its scalability. Here you see a very simple depiction of a scale-out architecture. We have multiple application servers which are replicas, and requests can be sent to these replicas via a load balancer, which selects which one to send a request to based on the demand of each particular service. There's also a remote store called here as session store, and what this enables us to do is externalize all of the state which is managed by the application servers. So the application servers are what are known as stateless. They remember nothing about the conversational state they have with a particular client. Let's examine what that means in a bit more detail. The first essential component of our scale-out architecture is a load balancer. In this architecture, all user requests are sent to a load balancer, which chooses a service replica to process the actual request. Various strategies exist for choosing a target service, but they all have the core aim of keeping each resource equally busy. The load balancer also relays the responses from the service back to the client. Most load balancers belong to a class of internet components known as reverse proxies, which control access to server resources for client requests. As an intermediary, reverse proxies add an extra network hop for a request, and hence need to be extremely low latency in order to minimize the overheads that they introduce. There are many off-the-shelf load balancing solutions as well as cloud provider specific ones, and we'll talk about these their general characteristics in much more detail in a week or two. The other essential element of a scale-out architecture is a stateless service. For load balancing to be effective and share requests evenly, The load balancer must be free to send consecutive requests from the same client to different service instances for processing. This means the API implementation in the services must retain no knowledge or state associated with an individual client's session. When a user accesses an application, a user session is typically created by the service, and a unique session identifier is managed internally to identify the sequence of user interactions and track the session state. A classic example of session state is a shopping cart. To use a load balancer effectively, the data representing the current contents of the user's shopping cart must be stored elsewhere. It can't be stored within an individual service node. This elsewhere is typically a data store, or as we'll see soon, a cache. And this means that any replica service can access the state when it receives a request as part of the user session. So a request comes in from the user, it identifies the session, and the service then looks up the session in the shared data store. That means that the service is essentially stateless. Scaleout is highly attractive, as in theory, you can just keep adding new virtual hardware and services running on that hardware to handle increased request loads and keep request latencies consistent and low. As soon as you see latencies rising, you just deploy another service instance on new hardware. This requires no code changes and hence is relatively cheap. You just pay for the hardware you deploy. Scaleout has another highly attractive feature. If one of the services fails, then the requests it is processing when it fails will be lost. But as the failed service manages no session state on behalf of the client, these requests can simply be reissued by the client when it receives an exception. And the load balancer will send this request to another service instance for processing. This means the application is resilient to failures in the service software and hardware, thus enhancing the application's availability. Availability is a key feature of distributed systems, and one we'll discuss in depth in later sections. So while scaling out with stateless services is a fundamental principle for scalability, like any engineering solution, it has its limits. As you add new service instances, the request processing capacity grows, potentially infinitely. At some stage, however, reality will bite and the capability of your single database to provide low latency queries will diminish. Slow queries will mean longer response times for your client from the services they're calling. If requests keep arriving faster than they are being processed, some system components will eventually fail due to resource exhaustion, such as memory exhaustion, and clients will see exceptions and timeouts. Essentially, your database has become a bottleneck that you must engineer away in order to scale your application further. The easiest approach to provide scalability at the data tier with your databases is scale up. This means scaling by increasing the number of CPUs, memory, and disks in your database server. And this can go a real long way to scaling your system. For example, right now, if you go to Google Cloud Platform, you can provision a SQL database on a 96 node instance, which has 96 CPU node instance, which has 624 gigabytes of memory, 30 terabytes of disk, and can support 4,000 connections from services. And this will cost you somewhere between $6,000 and $16,000 a year, depending on the deal that you take. This really isn't a lot of money for scaling up your service. Large databases, though, need constant care and attention from highly skilled database administrators to keep them tuned and running fast. There's a lot of wizardry in this job. Database administrators are very highly skilled, specialized people. They know about query tuning, they know about disk partitioning, indexing, on-node caching, and hence database administrators are very valuable people that you want to be very nice to. They can make your application services highly responsive indeed. In conjunction with scaling up at the database tier, a highly effective approach is querying the database as infrequently as possible from your services. How do you do this? Well, it can be achieved by employing a distributed cache in the service tier. A cache stores recently retrieved and commonly accessed database results in memory, so they can be quickly retrieved without placing a burden on the database by requerying for results that we already have stored. For data that is frequently read and changes rarely, your service processing logic can be modified to first check a distributed cache. Typically, people use something called Redis or Memcached. These cache technologies are essentially distributed key value stores with very simple APIs. We'll see how this works on the next slide. Here you can see we've introduced a distributed cache at the service tier, and this will hold results which have been recently retrieved from the database or computations which we've calculated and don't need to recalculate frequently. A classic example might be a restaurant menu. It changes once a day, and the changes are committed to the database, and then whenever the menu is read by clients, we send them back the same information. We could store this within the cache such that when we need to satisfy a request for a new menu, we just retrieve it from the cache. We don't have to query the database. Accessing the cache requires a remote call from your service, as you can see here. But if the data you need is in the cache, this is done on a fast local network, and it's far less expensive than querying a database instance. Introducing the caching layer requires you to change your processing logic in the service to check for cached data. If what you want is not in the cache, your code must still query the database, and typically it will then load the results of the query into the cache so that it can be used by subsequent requests. You also need to decide when to invalidate or remove cache results. This depends on your application tolerance for serving stale results to clients and the volume of data you wish to cache. There are many strategies for doing this, such as least recently used and things like a time to live, whereby items are removed from the cache after they expire after a time limit. For example, in our menu in a restaurant, this may be 24 hours. A well-designed caching scheme can be absolutely invaluable in scaling your system. Caching works great for data that rarely changes and is accessed frequently, such as inventories, events, and contact data. If you can handle a large percentage, like 80% or more, of requests from your cache, then effectively you're buying extra capacity at your database because it's not being involved in handling many of these requests. Still, as systems grow and need to rapidly scale to access terabyte and larger data stores, then a single database essentially becomes infeasible. And here you can see on the chart the scale of data sizes that we're talking about here. Terabytes are very common nowadays, petabytes are not uncommon, and the internet companies are storing exabyte scale data stores. For this, we need something more than Scaleout. In fact, the only way to handle data stores of such magnitude is to introduce distributed databases. Here you can see in the diagram we have multiple disks, and these would be attached to multiple nodes, such that we can distribute the data across multiple nodes, each with their own disk. But logically, the database appears to the service as a single database. It issues queries, and the results come back from the database as if they would from a single database. However, because we can partition and spread data across multiple disks and multiple nodes, we can grow the database to immense sizes. There's a lot of distributed database technologies around. If you look in some of the information on the web, you'll find probably hundreds of them in 2020 when I'm recording this. It's a complex area and one we'll talk about much more later in this course. But in general, there are two general main categories. The first is distributed SQL stores from major vendors such as Oracle and IBM. These enable organizations to scale out their SQL database relatively seamlessly by storing the data across multiple disks that are queried by multiple database engines. These multiple engines logically appear to the application as a single database and hence minimize the amount of code changes you need to make when you scale out your SQL database, Still, there are typically features that in SQL that are not supported on a distributed database. The other approach is the so-called NoSQL data stores from a whole array of vendors, many of which you've probably never heard of. These products use a variety of data models and query languages to distribute data across multiple nodes running the database engine, each with their own locally attached storage. Again, the location of the data is transparent to the application and typically controlled by the design of the data model using hashing functions on the database key. Leading products in this area are Cassandra, MongoDB, Neo4j, Couchbase. There are many, and each of these implements a different data model and different API. So it's a complex world, the distributed database one. One of the really powerful features for scalability of distributed databases is that as the data volumes grow, distributed databases have features to enable the number of storage nodes to be increased. As nodes are added or potentially removed, the data managed across all nodes is rebalanced by the database engine to attempt to ensure the processing and storage capacity of each node is equally utilized. Distributed databases also promote availability. They do this by supporting replication of each data storage node, so that if one node fails or cannot be accessed due to a network problem, another copy of the data is available on another node. The models utilized for replication and the trade-offs these require, and we'll be talking a lot about these when we have discussions about consistency in a few weeks, are really important to understand when we design a distributed database. Also, if you're utilizing a major cloud provider, there are typically two ways you can deploy your data tier. You can choose to deploy your database using your own virtual resources, and build and configure and administer the database using your own administrators. So you're installing the software and you're managing the database. Alternatively, you can utilize cloud-hosted databases such as DynamoDB or Google's Firestore. These simplify the administration effort associated with managing, monitoring, and scaling the database, as many of these tasks essentially become the responsibility of the cloud provider you choose. So potentially these can really ease the administrative effort in scaling a database. But of course, the no free lunch principle applies here. Still, as systems grow, we have to adopt other strategies to enable them to scale. Any realistic system will have many different services that interact when processing a request. For example, accessing a web page on Amazon.com can require in excess of 100 different services being called before a response is aggregated and returned to the user. The beauty of the approaches we've described so far, namely stateless services, load balancing, and caching, and distributed data, is that we can just extend these core design principles and build a multi-tiered application. In fulfilling a request, a service can call one or more dependent services or downstream services, which in turn are replicated and load balanced. This approach of utilizing multiple tiers is illustrated in this diagram. Here a request arrives from the client to the load balancer. It distributes the request amongst multiple service replicas. Each in turn may make a call to a downstream service, which again is load balanced across multiple replicas, each with caches available. These may or may not query the database and then return the results through the upstream tiers to the client. And we can essentially keep adding tiers here as our application scales. This multi-tier design also promotes utilizing multiple services within the same tier. So here, for example, a request arrives from the client, and based on some elements of the request, the load balancer chooses to distribute the request to either service 1 or service 2. And these in turn may make calls to downstream services that access the database. The power of this design is that it promotes having different load balanced services at each tier in the architecture. For example, on the previous slide, we had two internet-facing services, each of which utilize underlying core database services. Each service can be load balanced and employs caching to provide high performance and reliability. Let's say one of these services was available to provide the features available for web browsers, people accessing the application through the web, and another was available for mobile application users. This is important because the two user interfaces may have a different set of features. The beauty of this approach is that we can then scale each service based on demand, such that if the number of mobile services users grows, we can scale that service independently of the services available for the web browser, which may experience a decreased load, in which case we can scale it back and just reduce the number of replicas we have. This sort of approach is called the back-end for front-end pattern, and it's a very common approach within scalable services. One we'll talk about a little bit more as we start to move towards microservices later in the course. Finally, let's talk about responsiveness, or improving responsiveness. Most client requests expect a response. A user might want to see all the auction items for a given product category, or see the real estate that's available for sale in a given location. In these examples, the client sends a request and waits for a response to be received. The time interval between sending the request and receiving the results is called the latency of the request and is illustrated on the slide here. We can decrease latencies by using caching and pre-calculated results, as we've already discussed, but still many requests will still result in a ultimately relatively slow database access. A similar scenario exists for requests that update data in an application. As an example, let's assume a user updates their delivery address immediately prior to placing an order. This means the new delivery address must be persisted in the database so that the user can confirm the address before they hit the purchase button. The latency in this case includes the time for the database write, which is confirmed by a response to the user before they actually make their purchase. Some user requests, however, can be successfully responded to without fully persisting the data in the database. So, for example, users may favorite a product in a catalog, or they may add a song to a playlist or update their GPS location as they're driving along. None of these results are needed immediately by the client, and hence we can exploit this use case to improve the responsiveness of our applications. Essentially, the data about the event is sent to the service, which acknowledges the receipt of the request and concurrently stores the data in a remote queue, which the data is then retrieved from subsequently and written to the database. Writing some data to a message queue is much faster than writing to a database, and this enables the request to be successfully acknowledged much more quickly by the service. We then need another service which is deployed to read messages from the queue and write the data to the database. When the user subsequently comes back and checks that what songs are in their playlist, the data should have been updated. The key here is that the data gets updated eventually. This is illustrated in the figure here, whereby requests flow to our services here, but instead of writing to the database for certain types of requests, they'll write to a queue. Here the queue stores the pending messages for update, and then some consumers retrieve those messages from the queue and make the updates to the database. But while that's happening, the request has been acknowledged back to the client as being successful. So basically the application is making a promise to the client that it will eventually update the database. This request processing pattern can be utilized whenever the results or writes are not immediately needed by the use case. Many queuing technologies exist that applications can utilize, and we'll discuss how these operate in much detail in later sections. These queuing technologies basically all provide asynchronous communications. A producer writes to the queue, which acts as temporary storage, while another consumer removes messages from the queue and makes the necessary updates to the downstream database. So the key here is that the data eventually gets persisted. Eventually means different times in different types of applications. It may mean a few seconds or a few milliseconds. The key is that it eventually gets updated. When you design application scenarios like this, though, you have to make sure the use case is resilient to longer delays, such that if the user does query for an update's value and it's not been persisted, such a song been added to their playlist, it's not the end of the world. We know it will appear eventually. So, in summary, this section has provided a whirlwind tour of the major approaches we can utilize to scale out a system as a collection of communicating services and distributed databases. Much detail has been brushed over, and as you almost certainly know, in software systems the devil is in the detail. So in subsequent sections we're going to start progressively exploring these details, starting with some fundamental distributed system capabilities and characteristics, and then we'll focus on services and load balancing and caching and queuing, and then finally move to distributed database technologies and the underlying distributed theory that's necessary to understand to make all these systems work.